Hello everyone. In today's lesson, we're going to be learning about derivatives of logarithmic and exponential functions. So to begin with, we're going to have a couple new rules that we're going to be learning. So the first one is that if we take d dx of the natural log of x, this is just going to be equal to 1 over x. Our second rule is that if we have d dx of the natural log of some u function, which u is just a function of x, this is going to be using the rule we just had with the natural log of x, except for now we're going to have to use the chain rule. So this is going to end up being 1 over x times the derivative of u, which then of course we would just write as u prime over x. For the third rule, we have d dx of some log function with base b of x. This is just going to be 1 over x natural log of whatever your b is for your base. And then like before, our fourth rule is going to be if we have d dx of some natural or some log base b of some u function, which again is in terms of x, this is going to be the same idea. It's going to be 1 over x natural log of b, but now we have to use our chain rule. We take the derivative of what's inside the log, and this is going to be u prime, which then of course we can rewrite as u prime divided by x natural log of b. Another useful thing to understand is the number e as a limit. So our number e, which is Euler's number, can be written as the limit as x goes to 0, 1 plus x to the 1 over x power. And then what's happening is as this goes to 0, right, we have 1 plus x. This x term, of course, is approaching 0 as our power is going to 1 over 0, which means that it's approaching infinity. So this is going to get, this term is going to approach 1 as this approaches infinity. And this is equal to, if you wanted to do it in terms of as n goes to infinity, you could rewrite this as the limit as n goes to infinity, 1 plus 1 over n to the nth power, which if you kind of look has the same properties, right? As x goes to 0, this makes this 1 plus 0. As n goes to infinity, this is equal to 1 plus 1 over infinity, which is going to be infinitesimally small, basically 0. And of course, as x goes to 0, this power goes towards infinity. As n goes towards infinity, this power also goes towards infinity. So let's do some examples based on these new rules that we've just learned. So the first is we want to differentiate y equals the natural log of x cubed plus 1. So looking at our rules, whenever we take the derivative of the natural log of some function with in terms of x, this is going to end up being 1 over whatever's within the natural log. So this is going to be x cubed plus 1. And then we're going to take the derivative of whatever's inside. So of course, x cubed, we're going to use our power rule, is going to be equal to 3x, and then plus the derivative of 1, derivative of a constant, is equal to 0. And we're left with 3x squared over x cubed plus 1, right? Because when we did our power rule, we brought down the 3, and then we subtract 1 from the power. For our second example, we want to take d dx of the natural log of sine of x. So as before, when we have the derivative with respect to x for natural log, we're going to take whatever's within the natural log, and we're going to have 1 over that. So 1 over sine of x. And then we're going to multiply it by the derivative of what's inside, again, using chain rule. So the derivative of sine of x is going to be cosine of x. So this will be cosine of x over sine of x, which if you remember, we have that one identity we talked about before. We had tangent of x is equal to sine of x over cosine of x. Well, similarly, cotangent of x is equal to cosine of x over sine of x. So we can actually rewrite this as cotangent of x. In fact, these are the kind of identities that will actually help you show or solve for a lot of the other derivatives we looked at previously, the trigonometric ones, because a lot of times what you can do is you can use these identities to change things like secant, cotangent, tangent into sines and cosines. You can do rearranging things, eliminating different terms, and then getting it in terms of the derivatives that we learned previously. What about if we have the function f of x equals the square root of the natural log of x? So in this case, we're going to be using our chain rule. So first thing I want to do is I want to change this to the natural log of x to the 1/2 power, right? So this whole thing is to the 1/2 power. Now what we could do is we could do our chain rule, which is to say we pull the 1/2 down. So we take the derivative of x, f of x, so f is equal to, we bring down the 1/2, so we do 1/2 natural log of x, and then subtract 1 from 1/2, we get minus 1/2 power, and then we take the derivative of the inside term, which is natural log of x. So we said the natural log of x is equal to 1 over x, so this is going to give us times 1 over x. Now rewriting this, what we're going to get is we have 1 over 2, so I'm going to create my fraction here. We have a 2 at the bottom. Natural log of x to the negative 1/2 is the same thing as saying 1 over natural log of x to the 1/2, which is the square root. So this is going to be the square root of the natural log of x. And then, of course, we have this times 1 over x. So I'm just going to slide that in front of our square root. And this is, we have nothing else on top. I'm just going to put the 1 there. So we have that this is equal to 1 over 2x times the natural log of, or times the square root of the natural log of x. For our next example, we have the function f of x is equal to log base 10 2 plus sine of x. So looking at our rule that we have over here, this is going to be equal to, so the derivative d dx of natural log of base b u is going to be u prime over u natural log of our base b. So in this case, if we were to solve this, our u is the 2 plus sine of x. So this is going to be 2 plus sine of x. This is going to be our u. And then this is going to be times the natural log of our base, which is going to be, in this case, natural log of 10. And then now in the top, we have u prime, which is to say the derivative of the inside term, right? So you can think of this as 1 over whatever is inside times the natural log of whatever the base is times the derivative of the inside, which means we can just put it on top of the fraction. So we're going to take the derivative of 2, that's going to be a constant, derivative of constant is equal to 0. Then we take the derivative of sine of x, we get cosine of x. So our answer for this one would be cosine of x over 2 plus sine of x times natural log of 10. For our next example, we want to find the derivative d dx of the natural log of x plus 1 divided by the square root of x minus 2. And I'm actually going to show you doing this multiple ways because I want to actually show that you can approach these problems different ways and still come out with the exact same answers. So the first way is, before we even touch the derivative, we can actually use some rules of our natural logs, which is to say that if I have the natural log of some function f of x times g of x, this would be the natural log of f of x plus the natural log of g of x. If I have some natural log of f of x over g of x, right? So this would be our f, this would be our g. This is going to be the same thing as saying the natural log of f minus the natural log of g. So we actually could treat this as d dx natural log of x plus 1 minus natural log of the square root of x minus 2. So this is one approach we could take. So now instead of having to do the quotient rule, we could actually use this natural log rule, which allows us to make it a lot simpler. But just to show they come out to the same thing, I'm actually going to also do the quotient rule. So we have, this is our f term for the quotient rule, and this is our g term. And if you remember, this is going to be g f prime minus f g prime divided by g squared. So then if we were to use our quotient rule, we leave our g alone. So this is going to be, I'm going to set it as power. So this would be x to the minus 2 to the 1/2. X minus 2 to the 1/2 power times. Now we take the derivative of our f term. So x plus 1, we take the derivative of that. Derivative of x is 1, and derivative of 1 is 0. So this is just going to be times 1 minus. Now we're going to leave our f term alone. So this is going to be x plus 1 times the derivative of the square root of x minus 2. So x minus 2 to the 1/2 power. So we're going to bring down the 1/2 x minus 2, and then the 1/2 power minus 1 is going to give us to the negative 1/2 power. And now we have to multiply by the inside, derivative of the inside. So the derivative of x is just going to be 1, derivative of 2, because it's constant, it's going to be 1, so this is just going to be times 1. And then this entire thing will be divided by g of x squared. So this will be x minus 2 to the 1/2 squared. Okay, so now let's actually rearrange everything a little bit. So first things first, we have x minus 2 to the 1/2 times 1. So nothing changes there. So we have x minus 2 to the 1/2, right? So the times 1 doesn't do anything. Then minus x plus 1 times 1 over 2 x to the negative 1/2 times 1. Okay, so what I'm going to do first is I'm going to pull that negative 1/2 forward. So this is going to be negative 1/2. And then I have x plus 1, x minus 2 to the negative 1/2 power. And then I'm going to just focus on the bottom here for a second. We have x minus 2 to the 1/2 to the to the second power. Well, whenever you're taking something like a to the power to another power, you're going to multiply those powers. So then 1/2 times 2 is just going to be to the 1 power. So this is going to be x minus 2. Okay, now if I were to actually look at this term here, this x plus 1 times x minus 2 to the negative 1/2, this is really kind of the same thing as saying, so we have x minus 2 to the 1/2 minus 1 times x plus 1, so x plus 1 divided by 2x minus 2 to the 1/2 power. So what we need to do in order to solve for this, we're going to have to get this first term over 2x minus 2 to the 1/2 power. So what we're going to do is we're going to multiply this one by 2x minus 2 to the 1/2 power over 2x minus 2 to the 1/2 power. And then, of course, this entire thing is still divided by x minus 2. Okay, so now when we do this, look what happens here. So this entire thing will be over 2x minus 2 to the 1/2 power. And at the top, we have 2x minus 2 to the 1/2 times x minus 2 to the 1/2. You add the 1/2s together, you get 2x minus 2 to the 1 power, so just 2x minus 2, plus x plus 1. And then this entire thing is divided by x minus 2. We can think of this x minus 2 as x minus 2 over 1. Doing fractional division means we're going to do multiply by the reciprocal. So this term is going to come into here. This 1 is just going to go up to the top, which isn't going to change anything. And then I'm also, while I'm doing this, I'm going to distribute this 2. So this is going to be equal to 2x minus 4 plus x plus 1 divided by 2x minus 2 to the 1/2 power times x to minus 2. So you can think of this as x minus 2 to the 1 power, which you add those together, you get to the 3/2 power. So this bottom part is going to be 2x minus 2 to the 3/2. Okay. And then simplifying this, we have 2x plus x. This is just going to be 3x. And then minus 4 plus 1 is going to be minus 3 over 2x minus 2 to the 3/2 power, which will then end up being, okay, so this isn't quite what we were expecting. But if you remember, this is just the derivative for this inside term. And when we have the natural log on the outside, remember, what we have to do is we have to take, when we're taking the derivative, which in this case is going to be d dx, this entire thing, it's going to be 1 over x, in this case, actually u. So 1 over u, I didn't mean to put that x, I don't know why I keep putting x's there. 1 over u over the derivative of u. So this is our derivative of u. So when we take the derivative of the natural log of x, then so this d u of that natural log of whatever we had inside, which was all of this, right? That's the derivative of the inside, is going to be u prime, which is going to be x minus 5 divided by 2x minus 2 to the 3 halves, and then divided by u, which in this case is going to be x plus 1, x minus 2 to the 1 half. So again, we're going to do fractional division. So this term is going to come to here. This term is going to come to here. We're going to get x minus 5 times x minus 2 to the 1 half divided by 2 x minus 2 to the 3 halves times x minus 1. Okay, so now if we look at this, we have x minus 2 to the 3 halves divided over underneath x minus 2 to the 1 half. So we could actually subtract these, right? So we would get x to the 1 half minus 3 halves, which would leave us with, right? So if we had x minus 2 to the 1 half minus 3 halves, this would leave us with 2 over 2. So this term is just going to go to x minus 5 divided by 2 x minus 2 x minus 1. And then, of course, if we wanted to make this look like what the answer will look like when I do the other approach, this is just going to be equal to x minus 5. We distribute the 2 into here. This becomes 2x minus 4 x minus 1. So that was a lot just to get this derivative. But now let's go do it this way that we had before. We had the derivative of, we took the natural log of the top term over the bottom term becomes the natural log of the top term minus the natural log of the bottom term. So let me clean this up and let's do that one. And I'll show you that it ends up being the exact same thing. X minus 5 over 2x minus 4 times x plus 1. Okay, with a clean slate, we're back to our starting point. Now we're going to take the derivative of natural log of x plus 1 minus natural log of square root of x minus 2. So we're going to distribute our derivative, and this is going to become d dx of the natural log of x plus 1 minus d dx natural log of x minus 2 to the 1 half power. So when we take our derivative of natural log of x plus 1, this is just going to end up being 1 over whatever is inside, so x plus 1, and then times the derivative of x plus 1, that's going to be just equal to 1, minus. Okay, so now again, we have a split point where we can do two different things. The first thing we could do is we could do the chain rule for this, right? So we take the natural log of, so this is going to be 1 over whatever is inside, so this will be x minus 2 to the 1 half times the derivative of the inside. Well, the inside is just going to be a chain rule, so this is going to be 1 over 2 x minus 2 to the negative 1 half, and then we multiply by the derivative of the inside, which is just going to be equal to 1. So now we have our derivative of our first term and the derivative of our second term. So in order to bring them together, what we need to do is we need to get them both in terms of the same denominator. But first thing I'm going to do is we have this right here. We have x minus 2 to the 1 half power, which is the same thing as saying 1 over x minus 2 to the 1 half power. So I'm actually going to put this in the bottom as x minus 2 to the 1 half. So whenever I multiply these two out, right, x minus 2 to the 1 half times x minus 2 to the 1 half, or x minus 2 to the 1 half squared, this is just going to become x minus 2. So we have this equal to 1 over x plus 1 minus 1 half. So it's going to be 1 over 2x minus 2. And this is the place where I was telling you that now I want to get them in terms of the same base. So I'm going to multiply this one by x plus 1 over x plus 1. And I'm going to multiply this one by 2x minus 2 over 2x minus 2. And by doing that, we're going to end up getting 2x minus 2 minus x minus 1 divided by 2x minus 2 x plus 1. When we simplify this, 2x minus x is just going to leave us with x minus, oh, sorry, I forgot to distribute my 2. So this would be minus 4. Minus 4 minus 1 is going to be minus 5, right? 'Cause basically what I did is I took the 2 when I was doing this and I was distributing it, so it became 2x. 2 times minus 2 is going to be negative 4. And then last thing, just put it in the same form we had before. I will distribute this as we move it over. So this is going to be 2x minus 4 times x plus 1. So you'll see that we have the exact same thing we got last time. But we actually could have done this even easier. So let's go back to this step. For the derivative of the first one, we're not changing anything. So this is still just going to be 1 over x plus 1 minus. But whenever you have the natural log of something to a power, right? So let's say you have the natural log of a cubed, whatever a is. What you could actually do, actually, let's just make it x, just make it simple. You can actually pull this cube out, and this becomes 3 natural log of x. Sorry, x, I mean. So what we're going to do in this case is this is going to be the derivative of, so let's rewrite this, d dx of, where am I at? So I'm going to pull this 1/2 out. So this would be 1/2 derivative of natural log of x minus 2. So now when we do this derivative, this is going to be a lot simpler to do, right? Because minus 1 over 2. When I take the derivative of natural log of x minus 2, it's going to be 1 over x minus 2. And then the derivative of the top, the inside is going to be derivative of x, which is 1. Derivative of a constant is 0, so it's just going to leave us with 1, right? Because 1 times 1 plus 0. And that leaves us with 1 over x plus 1 minus 1 over 2x minus 2. And if you look at right here, this is exactly what we had before we did our multiplication. 1 over x plus 1 minus 1 over 2x minus 2. So you actually see that there's multiple steps we could have diverged and done different approaches, and we end up getting the exact same thing when doing a problem like this. Now we're going to add one more rule to the mix. If we have d dx, so we're taking the derivative of our inverse tangent function of x, this is going to be equal to 1 over 1 plus x squared. So we're going to do one example just to kind of show how we would take this derivative. So let's say, for example, that we had y equals 1 over the inverse tangent of x. So what we could do is you could do your quotient rule, right? Treating this as f, which of course, you take the derivative, it's just going to be equal to 0. So it'd be not too difficult, and treat this as g. Or we can take the fact that if we have a negative power, it's the same thing as putting something into the denominator, especially if we have this, in this case, to the first power. So I can actually write this as the inverse tangent of x to the -1 power. So now when I take my derivative, I'm just going to be using the chain rule. So I'm going to bring down my -1, and then I'm going to leave the inside alone. So tangent inverse, or inverse tangent of x. Subtract 1 from this, to the -2 power, times. Now we need to take the derivative of the inside. Well, we just said that the inverse tangent of x has a derivative of 1 over 1 plus x squared. So this will be 1 over 1 plus x squared. So now rewriting this, we have -1 in the top. This negative power is going to bring this tangent to the bottom, the inverse tangent. And then we have times 1 over x plus 1 squared. So here, just keep it simple so we can kind of keep it situated. I'm just going to put this as 1 over 1 plus x squared. And then, of course, we could just combine this. I just kept it separated, but realistically, it's the same thing as -1 over the inverse tangent of x squared times 1 plus x squared. And that's really all there is to it. I just wanted to show you kind of a brief example of using this derivative in just anywhere that you had an inverse tangent of x. Whenever you take the derivative, whether you're doing it within a chain rule, product rule, whatever, it's just going to end up being 1 over 1 plus x squared. And then just like any other time, you now have this denominator term. If you're trying to add or subtract to it, like you're doing the product or quotient rule, you'd have to get it in terms of like base. If you are doing something like this, where it's multiplication, you just honestly write it out. So unless there's some cancellation, which there's nothing up top to cancel with, this is our final answer. And that's all there is to it. Thank you for watching. To continue learning, click the linked video here for the next lesson. If there's a topic you'd like me to cover, let me know in the comments. Don't forget to subscribe, and I'll see you in the next video.